In this presentation, we are going to talk about parallel training. Today, large language models are too big to train in single GPU. So, we have to know about parallel training technique to train large language models. In parallel training, there are two types of approach. First is model parallelism, that each GPU handles a different portion of the model. In this picture, the model has 4 layers and each GPU handles only one layer. Second is data parallelism, that each GPU handles different portion of data. In this picture, total batch size is 16 and each GPU handles only 4 batch size. Furthermore, in model parallelism, they also have two types of approach. First is pipeline parallelism, which split model by a layer. In this picture, GPU1 handles layer 1, 2, 3, and GPU2 handles layer 4 and 5. Second is tensor parallelism, which split model by a tensor. In this picture, GPU1 handles upper tensor of all layers, and GPU2 handles lower tensor of all layers. In Megatron-LM paper, they introduced an efficient tensor power approach to train transformer-based model like GPT or BERT. Before we get started, let's look at two types of matrix multiplication parallelism, which is the basic concept of Megatron-LM. First is column parallelism. This parallelism splits matrix by a column. In this picture, they split matrix A by two column matrix A1 and A2. They compute each submatrix independently and aggregate each output Y1 and Y2. Second is row parallelism. This approach split matrix by row. In this picture, they split matrix A by two row matrix A1 and A2. They also compute each submatrix independently and aggregate each output at last. In Megatron-LM paper, they partition 4 types of layer. First is MLP, and second is self-attention. Those two layers are the main blocks of transformer. Third is embedding layer, and last one is loss function layer. First, let's look at MLP. MLP has two linear layers, XA and YB. So they use column parallelism in first multiplication and directly use row parallelism in second multiplication. And at last, they aggregate each output Z1 and Z2. Second layer is self-attention. Self-attention layer has one attention layer and one linear layer. First, they split attention layer by scale dot product attention. In this picture, each GPU handles one scale dot product attention and directly use row parallelism in linear layer. And last, they aggregate each output same as MLP. Third is embedding layer. Embedding layer split by sub-embedding layers. In this picture, they split embedding layer into two sub-layers. First layer embedding A to M word, second layer embedding N to Z word. The word will be masked if it is out of the range. For example, in this picture, Korea will be masked in sub-layer 1 because sub-layer 1 handles only A to M word. Last layer is loss function layer. To compute loss value, we need to pass projection layer, which is transpose version of embedding layer. They split projection layer same as embedding layer. First layer project hidden vector which has A to M target word, and second layer project hidden vector which has N to Z target word. For example, hidden vector of subway will be masked in sublayer 1 because they handles A to M target word. So far, we have looked at prior training. Next, let's look at implementation. In implementation, I use two PyTorch modules. First is distribute module, which provides communication between processes. Second is multiprocessing module, which provides spawning process. Now let's look at layer implementation. In attention layer, every GPU calculates attention layer, and they aggregate each output by or reduce operation. And also in MLP, they aggregate by or reduce operation when every GPU finish calculating output of MLP. Second is embedding layer. First, each GPU mask token which is out of the range, and aggregate by or reduce operation when all GPU calculate embedding vector. Last is loss function layer. Same as embedding layer, each GPU mask hidden vector which is out of the range, and aggregate loss value by or reduce operation when all GPU calculate loss value. Finally, let's look at test code. First, we predict the output. Second, we calculate loss value. Third, we compute gradient value. And last, we optimize parameter. And this test code runs well without any error, so I hope that this code works well in real power training environment.